Hello friends, this is Manish Khandelwal. I have come again with your channel Brainy Builders. As you may be knowing that I post presentations suitable to school going children on this channel. These days I am posting presentation on science subject for class 10th students. There is a subject with title Light, Reflection and Refraction in class 10th science book. My last presentation was on mirrors which reflect the light. This is my second presentation on light subject and I shall be discussing about lens in this presentation which refract the light. So let's start. So to begin, let's once again read the properties of light. The first property is light travels in straight line. Second is speed of light is 3 into 10 to the power 8 meter per second, or we can say 3 lakh kilometer per second. This is the second property. Third is light travels as particles and wave. Fourth, if light falls on opaque surface, it casts shadow on the other side because the light travels in straight line. So the light cannot pierce the opaque surface, so we'll get the shadow. And last is no medium is required for light to travel. Let us understand refraction first. Bachcho, there are many mediums around us like air, water, glass, and the speed of the light is different in different medium. If you recall, we studied that the speed of the light in air is 3 into 10 to the power 8 meter per second. So in glass it will be different. And this causes light to change its direction when entering from one medium to another medium. And this process is called refraction. You may see this diagram where the light is entering from air to glass. Because the speed of the light has changed in glass, so the ray has changed its direction. And this is refraction. We can say this is a refracted ray now. And again, when the ray is exiting out from glass to air, it is again changing the direction. We'll study more about it. Had this glass slab not been there, the light ray would have gone in this direction, straight. But because of the glass slab, it has refracted first and then second time. Though it is parallel to this, but there is a displacement. You can see here. And this displacement due to refraction depends upon the refractive index of the medium, that is refractive index upon the glass here, and of course the thickness of the glass slab. Let us understand the laws of refraction. We have already studied laws of reflection. Now we study laws of refraction. Again, there are two mediums, air and glass. The light ray is hitting the glass here at this point. So this can be called incident ray. If you draw a perpendicular from a point where it is changing the medium, so it is changing from air to glass, it is changing the medium here. If you draw a perpendicular here, then the angle between normal and incident ray shall be called incident angle. And similarly, now the light ray has refracted because of the change in medium and change in light speed. So the angle between the normal and the refracted ray shall be called refracted angle. And what are the laws? Incident ray, refracted ray and normal, all three shall fall in the same plane. Like in the case of law of reflection, incident ray, reflected ray and normal, they were all in the same plane. The only change is here it is refracted ray. And second law is that the ratio of sine of incident angle and refracted angle is constant for a given color of light. You please note it down. Given color of light. We'll study about it more later. But when we are remembering the laws, then ratio of sine of incident angle and refracting angle is constant for a given color of light rays and given pair of media. So what can we say here? Sine theta I, ratio of sine of incident angle. So sine of incident angle is sine theta I and refracted angle is sine theta r. So sine theta I upon sine theta r is equal to constant. And this is also known as Snell's law. So these are the two laws of refraction. Now let us understand the nature of refraction. We can see these two diagrams here. One of course is on the top side, it is a rarer, that means it is less denser, and the bottom one is more denser. You can consider air and glass. Air is surely more rarer than the glass. Glass is more denser. So what is rarer and denser? But if we say that we have a box of 1 meter by 1 meter by 1 meter, that is the volume of the box. If we fill the one medium in this and we wait, and then we fill another medium there, and then we wait. So the weight is more for a denser medium. For example, in 1 meter by 1 meter by 1 meter, if we fill air and we wait, and then for example this is glass, then in 1 meter by 1 meter by 1 meter we fill glass. Obviously we can see that the weight of the glass will be more, so we can say the glass is more denser. Similarly, if we say water and glass in the same volume, if we fill water first and then wait, and then we fill the glass and then we wait, so whatever medium is having the more weight will be more denser, right? So here of course we see this is air, it is rarer, and then it is entering into the glass, which is heavier, which is denser. So the nature is when any ray is entering from rarer medium to denser medium, it bends towards the normal. And from where the normal is drawn? The normal is drawn from the point where the incident ray is changing its medium. So the incident ray is coming from air, it is hitting the glass here. Now it is changing the medium. From this point we draw a normal. We'll see that the light ray has bent towards this normal, and this is the refraction and this is refracted ray. Similarly, opposite, if the light ray is entering from glass to air, so upper side is denser and lower side is rarer. In this case, the point at which it is exiting out, we draw a normal. Then the angle between normal and incident ray, of course, is angle of incident, or incident angle we can say, and this shall be angle of refraction. Here the refracted ray will be moving away from the normal. Once again, when the light ray is entering from rare to denser medium, it is bending towards normal. when the light ray is entering from denser to rarer, it is moving away from the normal, and the normal is drawn from the point where there is a change in medium. So if the light ray enters from lower refractive index, that is rarer medium, to higher refractive index, that is the denser medium, then it leans towards normal and vice versa, right? Then what if refractive index, we just referred it, refractive index. So the refractive index is ratio of velocity of light in given pair of medium. There the medium was air and glass, right? So if we say that what is the refractive index of medium 2 with respect to medium 1? Please be careful here. Refractive index of medium 2, we'll write first here. With respect to medium 1, we'll write it here. Then velocity of light in medium 1 here divided by velocity of light in medium 2. So if we have to find out the refractive index of medium 2, then the velocity of light will come here, and with respect to medium 1, then the velocity of light of medium 1 will come here. If we say that what is the refractive index of medium 1 with respect to medium 2, then we'll say velocity of light in medium 2 divided by velocity of light in medium 1. Correct? One more thing, absolute refractive index. But your absolute refractive index is nothing where the one medium is air. In the previous slide, we have studied air and glass. So there, of course, the refractive index of glass will be called absolute refractive index. So here, of course, we say the light in the medium, or we say light in the glass. So refractive index of glass with respect to refractive index of air. This will be velocity of light in air divided by velocity of light in medium or glass. And here, of course, this again, recall that velocity of light in vacuum is 3 into 10 to the power 8 meter per second. Just for reference, the absolute refractive index of diamond is the highest, which is 2.42. Sometimes this question is asked that in which medium the velocity, the refractive index is highest. Then you will immediately write that the highest refractive, absolute refractive index is of diamond, which is 2.42. Let us study about lenses. But there are 4 types of lenses. One is concave lens, second is convex lens, third is plano-concave lens, and the fourth is plano-convex lens. You can see in concave lens and convex lens both the sides you can see are having curve, whereas in plano-concave lens one side is plane and another side is having curve. In plano-convex lens, again one side is plane and another side is having curve. We shall study only about concave lens and convex lens, where both the sides are having curve. You may recall that we studied 3 types of mirrors: convex mirrors, concave mirrors, and plane mirrors. If you see the shape here, concave lens, they are wider at the corners and thinner in the middle. Just opposite convex lenses, they are thinner at the corners and wider at the middle. Another important thing is that the concave lenses are diverging lens. That means when a light ray falls on a concave lens, it gets diverged because of the change in medium. If it is coming from air, for example, if it is this is made of glass, the medium is changing, the speed of the light will change, and the light ray will get refracted, and it will be diverging. In case of convex lens, when a light ray from air is entering into the convex lens, it will get again refracted, but it will be converging. So the concave lenses are known as diverging lenses also, and convex lenses are called converging lenses also. Let's see how a concave lens is made. Let us take a glass slab and cut two spherical shapes with a gap between the two. After that, if we cut and polish this surface also, this surface from the top, this surface from the bottom, then we get a shape like this, and this is what the concave lens is. The center of these spheres which have been cut are called center of curvature, and they are denoted with C1 and C2. We'll study about it later. Similarly, for the convex lens, again we take a glass slab. Again we cut two spheres here. The only difference is that in concave lens there was a gap between the two, whereas in convex lens these are intersecting, and this intersection is making a convex lens. This is the convex lens. Again, the center of spheres which have been cut from the glass slab are the center of curvature for convex lens. Now, few important definitions. One, of course, the center of curvature. As we studied just now, the center of the two spheres which were cut to make lens are called the center of curvature. So here, this was a glass slab. We cut two spheres here with a gap, and the center of each sphere is the center of curvature, C1 and C2. Similarly, for convex lens, we cut two spheres in this glass slab which are intersecting, and the center of each sphere is center of curvature of convex lens. Then another thing is the optical center. The middle point of the lens, this is white color middle point, here also it is white color middle point. This is known as optical center, and it is denoted by O. Another important term is principal axis. Friends, the imaginary straight line passing through both the center of curvature and the optical center. You can see here, this is the line which is passing through C1, C2, both the center of curvature and the optical center. Here also both the center of curvature and the optical center. This is imaginary because this is not the real line, but we can imagine that a line passing through both the center of curvature and the optical center. And this is known as principal axis. This is very, very important because all the images and our object all are going to be on this line only. Let us understand the rules for convex lens. And before talking about the rule, let us assume that the light ray is coming from air and falling on a convex lens which is made out of a different medium. This means that the light ray is entering from one medium to another medium. Its speed shall change, and as we have studied, the light ray shall get refracted. Now, the first rule is that when a light ray parallel to the main axis falls on a convex lens made out of a different medium, it gets refracted and passes through the focal point of the convex lens. It converges towards the focus lens, and that is why the convex lens is also called converging lens. Similarly, when a light is passing through the focal point of the convex lens, which is made out of a different medium, it gets refracted and gets parallel to the main axis of the convex lens. This is the second rule. Similarly, for concave lens, the first rule is that a light ray parallel to the principal axis of a concave lens get diverged after entering into the lens, which is made out of a different medium. And this ray appears to be coming from the main focus. And second rule is that a light ray which appears to be going towards the focal length of the concave lens gets parallel to the main axis after refraction. So these are the two rules for concave lens also. And the common rule for convex lens and concave lens is that when a light ray passes through the optical center of a concave lens or convex lens, then it passes through the lens without any deviation. You can see it here, it is not getting any deviation, there is no deviation here, as it is passing through the optical center of the lens. The lenses, of course, are made out of a different medium, but still, if the light ray is passing through the optical center, it will not deviate. Let us see how the images are formed with convex lens and concave lens. So let's start with convex lens. There can be 6 positions where an object can be placed in front of a convex lens to get the image. In the first case, let us assume that the object is at infinity. As in the case of mirror also, when the object is placed at the infinity, then all the incident rays shall be parallel to the principal axis. In this case also, all the rays coming from the object shall be parallel to the principal axis. As we have studied that rays parallel to the principal axis in convex lens shall pass through the focus point after refraction. So here also all the incident rays which are coming parallel to the principal axis shall be passing through focus point of the lens. We know that the image shall be formed at a place where 2 or more refracted rays are meeting. So in this case, the image shall be formed at focus only. So the position of image shall be at focus. The size you can see is a point, very small size. And since the rays are actually meeting, so the image shall be real and inverted. In remaining 5 cases, you will notice that from the object there would be 2 light rays. One, of course, shall be parallel to the principal axis, and second shall be passing through the optical center of the lens. And the one which is parallel to the principal axis shall pass through the focus point of the lens after refraction, and the second ray which is passing through the optical center will not deviate. So in the second stage, when the object is placed between the infinity and lens, of course before the center of curvature, in this case the rays shall be meeting between the focus point and the center of curvature on the other side. You can see it here. So here the position of the image shall be between C2 and F2, between center of curvature and the focus point on the other side. You can notice the size is smaller than the object, and the refracted rays are actually meeting here, so the image shall be real and inverted. So this is second stage. We further move closer to the lens. Now we are at center of curvature. If the object is placed at center of curvature, again two incident rays, one parallel to the main axis, second shall be passing through optical center. This shall be passing through focus point and there will not be any deviation here. These two refracted rays shall be meeting below C2. And if you see here, then the size of the object and the size of the image is same. So the image shall be at C2 on the other side. Size shall be same. Object size and image size is same. It shall be real and inverted. Now we further move closer to the lens. Now we are at between C1 and F1, between focus and center of curvature. Again, two rays will go from the object, one parallel to the main axis passing through the focus point, second through the optical center. Now these two refracted rays shall be meeting after the center of curvature on the other side, and the object size is now bigger. So here, if the object is placed between center of curvature and focus in front of the convex lens, then the position of the image shall be beyond center of curvature on the other side. Its size shall be enlarged and it shall be real and inverted, right? So these are two. Now we move further closer to the lens. Now the object is at focus point and two rays, one parallel to the main axis, it shall pass through the focus point on the other side, and second ray shall be passing through the optical center without any deviation. You can see now these two rays are parallel. So these two reflected rays are parallel and they will not meet. We can say they will be meeting only at infinity. And if they are meeting at infinity, their size is going to be very enlarged one. So if the object is placed at focus in front of a convex lens, then the image shall be at infinity. Position is infinity. The size is highly enlarged. And of course, it shall be real and inverted. Friends, the last position is between lens and focus. If the object is placed between lens and focus, you can see the parallel ray is passing through the focus point and the ray passing through the optical center. These two rays, you can see the gap is widening. So they will not meet, even at infinity, they will not meet. So what will happen? If we extend these two behind, we'll see that these are meeting behind the object. So in convex lens, there is only one case where the image is formed on the back side of the mirror. And since these are not actually meeting, the image is going to be imaginary. So the position shall be same side of object. The size is enlarged and it shall be virtual. It is not real. It shall be virtual. Only in one case, in convex lens, the image is virtual, and of course it is erect. It is not inverted, it is erect. Right? So these were the 6 positions where the object can be placed in front of a convex. Now we come to concave lens. There can be only 2 positions, one at infinity and another between infinity and center of curvature. So when the object is at infinity, the incident rays shall be parallel to the principal axis. And we have studied that if the rays are principal to the principal axis, then it will get diverged. In case of convex lens, they were converging at focus, but in this case, the rays are getting diverged. Yes, it will appear to be coming from focus. If we stand this ray behind, it will appear to be coming from focus. Similarly, another ray at the bottom, if it is falling on the concave lens, it is again getting diverged. If you extend that behind, it also will appear to be coming from focus. So the image shall be formed at focus point, but it is going to be imaginary because it is actually the rays are not meeting here. These are appear to be meeting here. So if an object is placed at infinity in front of a concave lens, then the position shall be at f1 same side. Then size of course shall be point only as in the case of convex lens, and the nature will be virtual and erect. There it was real and inverted. Here it is virtual and erect. The second position is if the object is between infinity and 0, center of curvature. In this case, again, one ray is parallel to the principal axis. It is hitting the concave lens and getting diverged. If we extend it behind, then of course you can see it is like this. Then second ray is going through the optical center without any deviation. If we are extending this, then we are seeing that these two rays appear to be meeting here. Again, in this case, the position of the image shall be between focus and optical center. It is smaller than the object, and again it is virtual and erect. It is not real, it is virtual. So in this case, in case of concave lens, in both the cases, the image is virtual and erect. If you recall the convex mirror, in convex mirror there were two positions where the image was small and virtual. Here concave lens, you will find that in both the conditions the image is virtual and erect. So in convex lens and concave mirror, there are going to be 6 positions, or in concave lens and convex mirror there are going to be 2 positions. Let us have some formula for lens. One formula is 1 upon v minus 1 upon u is equal to 1 upon f, where u is equal to the distance of object from optical center, v is distance of image from optical center, and f is focal length of the lens. If you recall mirror formula, that was 1 upon v plus 1 upon u was equal to 1 upon f, and u was distance between object and pole, v was distance of image from pole, and f was the focal length of the lens. So this was the difference here. There it was plus, here it is minus. Then the power, the amount by which rays of light converge or diverge by a lens is called the power of that lens and is denoted by P. Exactly same as the mirror. There also it was P, and P was equal to 1 upon F. F is, if it is expressed in meter, if F is in meter, then the power shall come in diopter. It is same as in the case of mirror. And the third formula is magnification of lens. It is depicted by M. M is equal to H dash upon H, and this is equal to V upon U. In case of lens, it was minus V upon U. Rest all is same. So M is equal to H dash upon H, and this is equal to V upon U, where H dash is the height of the image and H is the height of the object. Let us understand few rules for taking distances. So these are quite similar to one we studied for mirror. So the first rule is that distances are taken with respect to O. This is the optical center. So all the distances shall be taken with respect to optical center. Like in mirror, we took all the distances with respect to pole. The second rule is that all the distances on the left hand side of the optical center shall be negative, and on the right hand side shall be positive. For exemplification, distance between O and center of curvature, or the optical center and focus, optical center and object, optical center and image. In this figure, all these distances would be negative. The third rule is that focal length for concave lens shall always be negative, and the focal length for convex lens shall always be positive. This is a similar case if you recall that focal length for concave mirror was negative and focal length for convex mirror was positive. So we can say that focal length for both concave lens and concave mirror is taken negative, and focal length for convex lens and convex mirror is always positive. Simple. Then height above the principal axis shall be positive. So if this object, we can say this height shall be positive, whereas height taken below the principal axis shall be negative. Say for if the image is made like this, so the height shall be taken negative. This shall be negative, this shall be positive. Above the principal axis shall be positive, below the principal axis shall be negative. So let us do some numericals. Let us solve few questions pertaining to lens. The first question is, which is a transparent medium that is covered by two surfaces out of which at least one is round? And the options are convex lens, concave mirror, convex mirror and plane mirror. But this is a simple question and the answer is in the first line itself. And it says that the medium is transparent. As you all may be knowing by now that we have transparent medium only in lens. So the option A is the right answer. Right? Then second question is, what shall be the nature and location of an object placed at focus in front of a convex lens? If you recall, we have studied that if an object is placed at focus point of a convex lens, then one light ray parallel to the principal axis shall pass through from the focus point of the lens after refraction. And the second light ray shall pass through the optical center and it will not deviate after refraction. Both these two lines shall be parallel. And where do the parallel lines meet? At infinity. So the image is going to be made at infinity. So the location of the image shall be infinity. And because these lines will be meeting really, so the nature of the image shall be real and inverted. Right? The third question. Speed of light in medium 1 is 2c and medium 2 is 3c. What will be the refractive index of medium 1 with respect to medium 2? Fine. We have studied if we have to find out the refractive index of medium 1 with respect to medium 2, we write N12, right? And this was equal to speed of light in medium 2 divided by speed of light in medium 1. So we have to find out the refractive index of medium 1. So it will go down, and with respect to medium 2 it will be up. So N12 is equal to speed of light in medium 2 divided by speed of light in medium 1. So it will be N12 will be 3c upon 2c, which will be equal to 1.5. So the answer is B, 1.5. Fourth question is, an height of an object is 5 centimeter. It is placed at a distance of 25 centimeter in front of a convex lens, having focal length of 20 centimeter. find as to where the image shall be formed, its nature and its height. But if you recall, we studied one formula for lens, that was 1 by V minus 1 by U is equal to 1 by F, where V was the location of the image from optical center, U was location of the object from optical center, and F was the focal length of the lens. So what we have to find out here, the image formed and nature. So we have to find out where the image is going to be formed. That means we have to find out V. So if we see here, 1 upon V will be equal to 1 upon F plus 1 upon U. What is F here? Focal length is 20 centimeter. The lens is convex lens. So in convex lens, the focal length is always positive. So F is going to be 20 centimeter. Great. What is U? U is, it is placed at a distance of 25 centimeter, and U is always minus. So U will be equal to minus 25. If we put the value here, it will be 1 upon V is equal to 1 upon 20 plus 1 upon minus 25. And if we solve it, V will be equal to 100 centimeter. Now, they are asking the nature and the height. So if we recall the formula for magnification, it was M was equal to H dash upon H, and it was also equal to V upon U. H dash was height of the image, H was height of the object, and V and U we know. So V here is equal to 100 centimeter, we put 100. U was minus 25, so it will be minus 4. In this case, H dash will be equal to minus 4 into H. How much is H? Height of the object is 5. So 5 into 4, minus 20 centimeter. So height of the image shall be minus 20 centimeter. And since it is minus, so it will be inverted. The image shall be inverted, right? Next question is, an object 4 centimeter in size is placed 25 centimeter in front of a convex lens of focal length 15 centimeter. Then at what distance from the lens would the should a screen be placed in order to obtain a sharp image? That means they are just asking where the image is going to be formed. V they are asking. They have given us U. U is minus 25. They have given us F. F is plus 15 because it's convex lens. Again, we use the same formula, 1 by V minus 1 by U is equal to 1 by F. So 1 by V is equal to 1 by F, and it will be plus 1 by U, but U is minus, so it will be minus 1 by 25. If you solve it, we will be coming as 75 by 2, that is 37.5. You can solve it. Then the size of the image, we use the same formula, H dash upon H is equal to V upon U. We know now V, we know U, we know the H also, height of the object, and we can find out H dash. And we have to make a ray diagram showing the formation of an image. So we know now what is U, we know what is V. U is minus, that means U is going to be on the left side. V is plus, it is going to be on the right side. And we can make the image, because image is bigger, it is enlarged image. The object was 4 centimeter and the height of the image was 6 centimeter. Fine. What are the properties of light? If you recall, we studied the properties of light. One was the light travels in straight line. Then the speed of the light in vacuum and in air is 3 into 10 to the power 8 meter per second. Then one thing more, it was light travels in particles and wave. Then if we put any opaque object in front of light, then we find the image of that object, because the light travels in the straight line. And of course, we don't need any medium for light to travel. It can travel without any medium. So these were the few properties of light. All these numericals can easily be solved. Our convex lens having focal length of 16 centimeter makes a 4 centimeter high image from 20 centimeter, 4 centimeter from lens. So they say focal length 16 centimeter convex lens. So f is equal to plus 16 centimeter. 4 centimeter high image. Here h dash is given. Height of the image is given here. And 24 centimeter from the lens. So they have given V here. V is 24 centimeter. Find as to where the object is placed. They are asking you. Nature of image and magnification. We apply same formula, 1 by V minus 1 by U is equal to 1 by F, and M is equal to V upon U is equal to H dash upon H. Same formula if we apply, we get the answer here. Then write 3 differences between concave lens and convex lens. Fine. So one difference was that concave lens is broader, wider at the end and narrow at the center, whereas convex lens is pointed or narrow at the end and broader, wide at the center. This was one. Then concave lens is diverging lens and convex lens is converging lens. Then we can say that in concave lens we always get only small and virtual images, whereas in convex lens we get both. In one case we get larger and the virtual image, and in all other cases we get real and inverted image. So these differences you can write. Then power of a lens is 1 diopter. What shall be its focal length? We know the formula, P is equal to 1 upon F, or we can say F is equal to 1 upon P, where P is in meter. So we see here F is equal to 1 upon P, that means 1 upon 1, that is 1 meter. And 1 meter is how much? 100 centimeter. So its focal length is going to be 100 centimeter. So A is the answer. Last few more questions. One is a diverging lens forms a virtual image with a magnification of 0.5. If the object distance is 6 centimeter, calculate the focal length of the lens. So it is diverging lens, that means it is concave lens. And what is given? Magnification is given as 0.5. Object distance, that is U, is given as minus 6 centimeter. What we have to calculate? We have to calculate the focal length. Now we know U and we know M. M is 0.5. So M is equal to V upon U, that is 0.5 is equal to V upon U, that is U is minus 6 centimeter. So V will become minus 6 into 0.5 is equal to minus 3. So we apply the same formula, 1 upon V minus 1 upon U is equal to 1 upon F. We know the value of V, which is minus 3, which is then U is equal to minus 6, and then we can calculate F. So F will come here as minus 6. That means it is a diverging lens, and concave lens will always have its focal length in minus. So it is minus 6. F is equal to minus 6. Next question is, a light ray passes through a convex lens parallel to the principal axis. In which direction will the ray bend after passing through the lens? We know it very well. When a light ray is parallel to the principal axis, then it bends toward the focal point, toward the principal axis in a convex lens. So in this case, the light ray shall be bending towards the principal axis. Next is, what is the term for the bending of light ray as it passes from one medium to another? Surely the bend of the term, this term will be called as refraction. Then what is the main difference between reflection and refraction? In reflection, the light bounces back, whereas in refraction, the light ray bends after the refraction. And the last question is, the focal length of a mirror and lens is minus 15 centimeter. What type of mirror and lens are they? Options are both concave, both convex, lens is convex, mirror is concave, or lens is concave or mirror is convex. So focal length of concave mirror and concave lens is always minus. Once again, the focal length of concave mirror and concave lens is always minus. So the answer shall be both concave. So thanks, bachon. This is the end of part 2. I'll be coming up with another part on dispersion, refraction, and few examples. Thank you very much.